Hello. So, by the way, how's the midterm? Was it hard? Was it easy?
I didn't think it was too bad, but time was a little tight. But
Oh,
like,
okay. See. But were there any questions that were confusing or everything was clear? Were there any ambiguities in the questions? Okay. I consider that as no. Good.
There was one I remember. I'm not sure if this was addressed in a lecture and I just missed it, but I wasn't sure what exactly an execution context meant. I think it had to do with processes or something.
Execution context. Okay. So this is, was this mentioned in a question?
Yeah, one of the questions had a couple answers about execution contexts and I think how they were related to PCBs and TCBs. I assumed it meant the same as execution state.
Yes, yes. Yeah.
Okay, that's what I assumed, but it used a different word, so I wasn't sure.
Okay. Good. Yeah, Ragul says MCQs were tricky. Were they tricky? Uh, let me see. Yeah, like I really liked that question where I realized you can use execv to create infinite loops in a program, but if you are smart, you can actually use execvs to do computation without doing any loops, without using recursion. And yeah, that was, I felt that was interesting. Uh, MCQs were tricky. Okay. Choose which are true or tricky. Yeah, and the one advantage of execv question, one advantage of that execv approach is like if you use recursion, for instance, there is a limit on the stack space, right? There are like certain number of times in which you can do certain number of call stacks that you can push onto the stack because memory is limited. Whereas if you use execv trick, it's almost infinite. Like you can, there is no way the program can ever terminate. Okay. And there is no way that processor can even detect that it's an infinite loop because the PC is constantly changing. So it's tricky. Cool. Yeah, like okay, so okay, I'll try to avoid those MCQs, like choose the correct answer, because I don't know if there is any other way in which we can test certain concepts. Uh, like I could have made them an independent questions themselves, but it would just, like the sheer number of questions would be too much. Like it could overwhelm students. So I thought I could group them in some way. Okay. So so the pattern will be almost kind of same, but I'll try to make sure that there are no ambiguities, and I'll maybe I'll see if I can give more time rather than 1 hour. I'll try to avoid those, or rather reduce those, like choose which ones are true questions. But I cannot promise. But I'll try to like reduce the quantity. Okay. So, oh, okay. How was okay? So, how many students, like how many of you think time was too short? Okay. 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 I see it was too short. I'll try to, uh, yeah, I'll try to increase the time like for finals. Yeah. And how was the, like, do you like these kind of questions, or do you think it's interesting to, uh, like have more coding questions, or like more true and false, or like more concept based questions, or like more coding questions, or like debugging kind of questions? Which kind of questions were interesting, or like would you prefer to see them in the finals, so that you don't need to like remember all the words and concepts, right? Okay, good. Okay, good. And see, oh, okay, the fork, I see the fork thing. Yeah, nice. In the finals, I wanted to like give some examples that I got during like office hours, some debugging questions that I got, some questions that I helped students with. I wanted to like simplify those examples and give them in the finals to see like if you can find a bug, or like debug this, for instance, message box implementation, debug this. Like, this is the behavior, this is the code, can you find the bug? So those kind of questions, I'm planning to include at least a couple of those questions in the finals. Of course, I'll give enough time so that you get enough time to think about those things. Yeah, I'll give more time. Good. uh, Very nice. Okay. So, and also one more thing, as you might have figured out from like lab 3, and if you have already started lab 4 and also lab 4, most of the time you spend would be in debugging. Okay. Writing code is easy, especially operating systems code. Writing, or like conceptualizing certain idea is very easy. Like page tables, they are very simple, right? You maintain a table, you do a translation, there you go. But when you try to implement it, it becomes really really hard. Like, you need to make sure that everything is synchronized, make sure that the memory is freed, and the interrupts are restored in every written path, so on and so forth. But this is not the case with other fields, such as, for instance, let's say algorithms. Okay, understanding the algorithm is hard. Okay, implementing it is, yeah, you get it, and it's kind of easy once you get the algorithm. Whereas in operating systems, it's the other way around. Concepts are very easy, but implementing it correctly is hard. Okay. uh, let's get to today's class. So today we'll be looking into file system abstractions. Yeah, this is one of my favorite topics. So, and also this is the first time when I started computer science, when I was introduced to operating systems. Our project was to implement a file system from scratch, and that was your homework, your lab for lab 5. But I'm not sure if we get to lab 5. But yeah, lab 5 was implementing your own file system. Uh, okay, so we have looked at various places in computer system that we can store memory, we can store our data, like registers, caches, main memory, and finally disk. So disk is at the bottom of the memory hierarchy because it's very slow and it takes the maximum time, like it takes more time to fetch data from disk. And it's another advantage of disk is it's persistent, like the data is stored across reboot, so even if you reboot the system, the data is still present. So in order to store the data, we need to have some mechanism which actually, like some persistent mechanism. So the persistent mechanism is usually the most commonly used and very fast persistent mechanism to store data is magnetic disks. So magnetic disks were like the first technology that came in. Not exactly first, but there were like capacitor tubes before. But one of the most successful technology where we could use magnetization to store data onto platters. Okay. So the way you store data is by writing small dots onto the platters. Like you can write dots onto the top or at the bottom. So here, a disk, like the classic magnetic disk, you have various platters. So each platter, the concentric circles are tracks, and each platter could be divided into sectors, and a block is a sector in a track that forms a block. And how is data stored on disk? Through files. So from user's perspective, we just store files on a disk. The files, actually we do store directories, but at the bottom, we just have files. Files have names and it has sequence of bytes. So we need a mechanism uh, to convert files to the magnetic dots onto the disk. So this is what file system does. Okay. So file system provides an abstraction where user accesses files and file system translate that to reading or writing these magnetic dots from the platter. So, and in order to do that, file system needs to store metadata along with the data that the file contains, right? Because file system needs to store the file name and the permissions because it needs to make sure that users don't access other users' files, and type of file. And finally, it also needs to store the list of blocks that contain the data of the file. Okay. So one thing to note here is on a disk, the unit of access is a block. So although you can store bits onto the disk, but disk itself provides an abstraction where the unit of access will be 512 bytes in most of the disks. But now it's actually 4 kilobytes in most of the SSDs. On modern SSDs, it's 4 kilobytes. So that is the unit of data that you can store or load from the disk. Okay. And so file system, for each file, it stores the file name and all the list of the blocks that contain the data that belongs to the file. So the structure of the data stored by the file system, it's called inode. So inode, it's literally a structure. Like if you go to Linux kernel source code, you actually would see struct inode, where you just store all the metadata in this C struct literally. And each inode contains all the contains the file name, permissions, owner, group, and type of files, and then finally list of disk blocks that contain data of the file. And where are these inodes stored? Again, these inodes are stored on the disk. Although the inodes are maintained by the file system, but the inodes themselves are stored on the disk. They're not stored in memory because we want the data to be persistent. So since inodes maintain the metadata for a file, they should themselves be stored on the disk. And usually what happens is you'll have a portion of disk that is dedicated to inodes. That way, like if you want to just read the files on the disk, you just go to that particular section of the disk and you just read all the inodes. That will give you all the files on the disk. Okay. So file inode, this is a typical inode structure. So as you can see, it has various fields corresponding to different data of a file. And finally, it contains a list of blocks where the content of each element is block number, which contains the data that belongs to the file. Okay. And finally, we also have indirect blocks and doubly indirect blocks. And this helps us to have huge file sizes, right? So without these indirect and doubly indirect blocks, we cannot, like there is an upper bound on the size of the file. Like if you have just a sequence of block pointers, then the maximum size of the file is defined by like, it will be very small because that's the total number of blocks into block size. Whereas using indirect and doubly indirect blocks, they allow us to expand the file size indefinitely. So what you can do is once you have indirect blocks, these are again pointers to additional blocks. And finally, at the bottom, you again can have another indirect block. Similarly, you could do the same thing with doubly indirect blocks. So this also shows that just the concept of indirection is so powerful that you can solve most of the operating system problems using just like one level of indirection. So let's look at a few examples. Let's look at the file system and see what happens in the file system. Let me share my screen. So you can see the terminal. You can see the terminal, right? Perfect. So let's, okay, there are many files on my desktop, for instance. So you can use stat to, okay, you can use stat to know the metadata of a file. For instance, let's say sender.c. Okay, so here, stat is a system call. Like if you do stat is a utility which actually does a system call to get information about a file. So when you give a file name to stat, it actually fetches the metadata that corresponds to that file. So here we are saying that the name of sender.c as stored by the operating system is sender.c, and it has inode number. This is the inode number, okay? And it is a regular file, okay? 853, okay, is the size, is the number of bytes in sender.c. And IO block, this is the block abstraction provided by the operating system, okay? And and 8 blocks are the disk blocks, okay? So there is like this is another level of abstraction provided by the operating system. These are actually disk blocks, okay? And this IO block is what operating system provides us. And so since this is the minimum size, like 4096 is the minimum size for any file that yeah, for every file for any file on Ubuntu, okay? So 4096 bytes is the size of IO block, which is provided by the operating system, and disk provides an abstraction where the number of blocks is 8. So this kind of says that the block size that is supported by the disk is 512, because if you do 512 into 8, that's 4096. Okay, that's why, like when you, let's say if you create, let me create an empty file, okay? Okay, this is an empty file I just created. So the size is 0. Let's do stat. Okay. So here, you see the size is 0, the IO block size is 4096. That is the size, that is the block that is allocated by the operating system. Okay, so basically this is to store the inode. And here the block size is 0, but let's say if I write 2 bytes, for instance, if I do stat, oh, you see the number of blocks is 8. Although I just stored 3 bytes, although I just have 3 bytes, the number of blocks assigned is 8. That means whenever you store data, the unit of allocation is 8 blocks, which is like 4 kilobytes. And the size, until you exceed 4 kilobytes, you always have the size of 4 kilobytes. That's why even if you go to the directory, even if you create an empty directory, the size will be 4 kilobytes. Okay. So each file has permissions. So there are, depending on files, there are 3 ways in which you can access files, principally. You have read, write, and execute. And who can access files? Either the owner, the user who created the file, or the group to which the file belongs, or the rest of, like the entire world belongs to the others category. So if you are an owner, there are certain set of permissions that are given to an owner, and there are certain set of permissions that you can give to the group to which file belongs, and you can define permissions for all the other users who are not owner or who don't belong to the group of the file. Okay. So permission bits. So there are 3 types of accesses and there are 3 entities. So we have 9 permission bits. And these, so you need 9 bits to store the permissions. First 3 bits are for the user, next 3 bits are for the group, and last 3 bits are for others, basically the users who are not users and who don't belong to the group of the file. The last 3 bits control the access to those users. And you can change permission of a file by using chmod, and you give the decimal corresponding to that bit pattern. So here 7 means 111 and 5 means 101. Like so. And to access file system, operating system provides various system calls like create, open, read, write, stat. So you can look at file permissions. Like, for instance, ls minus l, let's say send.c. So here, what I'm saying is here the owner is Mechery, okay, myself, and the group of this file is also Mechery, okay, and then I have read write. Okay, so I, the owner, have read write access, and others like the group, which is myself, has read write access. All the other people have just only read access. Okay. And so you can know the group of like the, uh, I hope you know what groups means. Like groups are basically a tag given to a set of users. So you can find your group by using groups, and let's say myself. So okay, I, like Mechery, my user ID, I belong to these groups. Okay. So, and groups allows you to give permissions to a group of users by assigning a file to certain group. Okay. And so next are directories. So directories, as you all know, it helps in organizing files. And similar to files, Directories themselves are also files, but the data inside directories is just a list of file name and inode numbers corresponding to that file name. Okay, they are just a list of file name and inode pairs. So, and there are, like, initially it was just single level directory, and then of course single level directories, there is not enough grouping, and the naming is inconvenient. And then we moved on to two-level directory, and eventually we ended up with three structured directories. That's what we use. So, and directories also have permissions, and directory permissions are tricky. And you could get into, like, if you don't set the directory permissions correctly, there are some interesting situations that you can face. Okay. So reading a directory, what it means by reading a directory is to read the contents of the directory file, or like read the contents of the data blocks inside uh, a directory, right? What does data blocks contain inside a directory? Just list of files. Okay. So reading a directory means you can list files inside a directory. That's the only thing you can do. Okay. What does it mean by writing to a directory? That means we can write into the data block that belongs to the directory. But what can we write? We can just write file names. So that means we can actually create some files, or create or delete files inside directory when we have write permissions. An interesting permission is executing a directory. Okay. So executing a directory allows, at very, like, precisely what it means is, executing a directory allows you to translate a directory to its inode number. Okay. What can you do with that? You can actually enter a directory. You can change your directory to a given directory if you have execute permissions. That's it. Note that execute permission is not exactly read permission, because you can have execute permission, but if you don't have read permission, then you cannot do anything. You cannot list the files. You cannot even write to a file. If you have execute only permission on a directory, it's pretty much useless. Okay. Let's see with an example, like how these different permissions vary. And this also, like, allows us to do some very nice, like, access control techniques. And, like, if you look deeply into Linux operating system as such, most of the things that Linux operating system enforces are just through file permissions, by the way. So let's look at directories. So here, what I have is, I have a directory which is execute only. I have a directory which is read only. I have a directory which is write only. Okay. So let's look at execute only directory. Oh, very nice. So execute only directory. Note that I can cd into execute only directory. However, I cannot list the files into execute only directory. Okay. Ls I cannot list because permission is denied. Now let's look at read only directory. Okay. So now let's go into read only directory. Can I do this? No, I cannot. Right? Because I cannot uh, I cannot access the, sorry. Uh, I'm sorry. Okay. So I cannot cd, I cannot change my directory to the read only directory because I don't have execute permissions. However, I can read only directory. That means, let's say, exactly, I can do this. I'm able to list the files. Okay. So ls was actually trying to access this file. Since I don't have access to those files inside the directory, that's why I get permission denied. But as you can see, I'm still able to read the contents of this directory. Okay. Now the interesting thing is write only directory. Okay. It's useless. Write only directory is kind of useless because what can you do? Okay. You can think that, okay, write only directory, what's wrong? I can, let's say, write only, let's say, dummy. Okay. You think that you should be able to do this, right? Because you have write access to the write only directory. But no, you don't, because so in order to, what happens is, in order to create a file inside some directory, you should first, operating system will actually read the contents of that directory first to see that that file doesn't exist. If it exists, it will try to use that file. Okay. If you don't have read access to a write only directory, then operating system cannot even know whether that file exists or not. So operating system says permission denied. Okay. So do you have any doubts? Read only directory is kind of useless. You cannot, you you just cannot do anything inside a read only directory, sorry, write only directory. uh, so any questions on the directory permissions of, see, okay. So let me see, let me open the chat. For some reason, when I share my screen on the monitor, it just freezes. It just becomes very slow. I need to do all sorts of this thing to, okay, let me open the chat window. Okay, could you sort of read and execute only by just testing what files exist or not? Uh, mm, mm, you, okay, read and execute only directly. So the thing is, you cannot, because when you try to, okay, so if you, no, you cannot do that, because when you try to open any file inside execute only directory, like by checking whether the file exists or not, uh, operating system, the written code that is written by the operating system is always constant. So is always like denied, irrespective of whether file exists or not. So it's hard for you to know, like there is no kind of like, there is no side channel for the user to understand whether the file exists or not. Because operating system, if you try to just read any file here, operating system will say permission denied, even though if file exists or not. So you cannot distinguish whether a file is present or not in an execute only directory. Jacob, does that answer your question? Execute only is, yes, it's almost useless, but you can at least change your directory. What happens when you change your directory is you can use the relative path, right? For instance, like if you do this, yeah, you can kind of do this relative pathing if you have execute only directory. But with respect to the access inside the directory, yes, it's pretty much useless. Yeah. Okay. So and another facility provided by operating systems is mounting. So you can operating systems allows users to mount certain file system at some other file in another file system. That this allows users to manage the entire, all the different disks by just using a single file system. Okay. So let's say you have two disks and you want to manage, like you want to access disks of the like you want to access files of the second disk, what you can do is you can mount file system like bar at foo. Then when you try to access foo, operating system redirects all the access to this file system corresponds to the bar. That way you can access all the disks by just looking at the root file system. And if you have ever used SSHFS, and that's exactly how this works. And even in your operating system, you could see many file systems that are mounted at different files. For instance, like you can look at, okay, use df. No. Okay. So you see, there are many file systems that are mounted onto your, like many disks that are mounted onto your file system. So if you do df -h, you could see that, for instance, yeah, dev, NVMe, this is like my flash disk, my SSD, partition one of that disk is mounted on like into /boot/EFI. Similarly, my partition 2, like P2 partition 2 is mounted on the root file system. Okay. And there are various other uh, directories where like loop, where there are other devices called loops. So loop devices are a way for the operating system to provide access to certain resources through files. Okay. Let's say if operating, does any, are you guys aware of like proc file system, for instance? Okay, so proc file system is a way in which you can communicate with the, like operating system can provide you some data regarding a process through files. For instance, you can like for each process there is a folder that is created by the operating system, and you can, let's say, this is self, means like the for the current process. So you can like see command line that the current process has run. Like this is bash command, like self is the current process. So you could actually see, this is almost like PCB of the process that is uh, maintained by the operating system. And you can actually see what operating system maintains for each process by going to proc file system. Okay. And this again is a file system mounted by uh, like file system that is mounted by the Linux kernel for you. Okay. And so can devices also be accessed using files? Exactly. So even all the devices are also files. Like in Linux, everything is a file. Like anything that you want to do will go through files. So these are all the devices. For instance, there are many devices. Few of these devices are virtual devices. Few devices are real devices. For instance, uh, so NVMe, this is my disk. Okay, this is my disk. Whereas there are certain, for instance, null device. This is just a device that if you read, you'll just get zeros. And like, and also, for instance, like you can, like if you read dev 0, you just get zeros. So dev 0, like try to read dev 0, just get zeros. That's it. You just get zeros. That dev 0 is a way for you to get zeros. And like, have you guys used dev random? So dev random is a way to get random data from Linux kernel. Okay, so there are many files that are provided by Linux kernel. Few of these are virtual, few of these correspond to the real devices. Okay, and okay, so yeah, let's look at links, like hard links and soft links, and then we can actually go through how to create a file system from the scratch. Okay, let's say, yeah, let's say given a disk, how does the file system work? Like how to create a file system from an empty disk. Okay, we can. I'll show a demo where starting from an empty disk. Okay, how can we create file system? What does each file system like? How does uh, like inodes are stored in the file system, so on and so forth. Okay, but yeah, let's quickly look at links first. So links are just file aliases. Uh, Here you can have two different files that correspond to the same inode number, or you can have one file that is just a pointer to the another file through file names. Like one example is hard link. Hard link is when you have multiple files with the same inode number. Okay, so here you can, when you delete one file, the other file would still be pointing to the same inode. That way you could avoid like duplicating the files. Let's say if you want to make an identical copy of a file, but you don't want to uh, like make a complete new copy, you can just use hard link. Okay. So, and since you can have hard links, so when you delete a file, operating system should be careful in order to delete the inode, because an inode could be pointed by multiple files. So it maintains a reference counting for each inode. When the count becomes 0, it will delete the corresponding inode from the disk, or rather like it will deallocate the inode. Symlink on the other hand, or like soft link, is a special file where the content of the file will be the path to which the file points to. Okay, so here bar is a symlink or soft link to foo. So here note that the inode number of foo and bar are different. However, the content of the bar file is the path to foo. Okay, so this allows soft links or symlinks to be created across file systems because there is no dependency on the inode. So bar can point to some file that belongs to completely different file system. Okay. Whereas in case of hard link, that's not possible because inode numbers are unique to a file system. Okay. So, and since if you change the inode number, since two file system could have same inode number, but they could correspond to different files. So that's why hard links cannot be made between files that belong to different file system. Whereas soft links, they can be like, you can create soft links across file systems because you store the link by the path. Okay. So let's look at quick demo of hard links and soft links, and then let's look at a complete demo of how we can create file, like how does a file system gets created starting from scratch. Okay. 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 So here, okay, let's say I want to create, let's say hard link to file one. The way I create is I use ln. I don't know the command, like I don't know the features for ln. Let's do ln man. Let's see what ln says. Okay, makes link between files. Okay, ln target and link name. Okay, very nice. So I do ln and let's say link name. Let's say I call it file name file1 duplicate txt, and this is my target, and this is my source file. Okay. Oh, I need to give, I think the target is this one. This is the link name. Okay. So now let's see what does aha. So you see file duplicate and file one, they have the same inode number. Okay. So here what I'm doing, what I just did is I created a hard link, which is file one duplicate, and which just points to the same inode as file 1. Okay, so here what happens when I delete, let's say, file 1. Okay. So here, if I delete file 1, everything still stays the same. I still have a file 1 duplicate that points to like file 1 duplicate that still contains the data of file 1, even though I deleted file 1. Okay. Now, let's create a symlink, which is a soft link. So here, let's see how to create symlink. Man, ln. Okay. I just need to pass s. Okay. Good. So let's say I create for file 2. Okay. Let me pass s to this. Okay. Here, okay. So here, as you can see, file 2, like ls was smart enough. It is displaying file 2 as a symlink to file 2 duplicate as a symlink to file 2.txt. And if you see the inode number of file 2 is actually different from file 2 duplicate is actually different from file 2. Okay. Data and file 1. Okay, so OS maintains, okay, I think Gray asked a question where like, how does OS knows when it can actually delete the data in file 1? Operating system maintains a reference count for each inode, where the reference count indicates number of files that are pointing to that inode. So even though when you deleted file 1, it did not delete the data of file 1 because the reference count is not 0, right? Because file 1 duplicate is pointing to that. That's how it'll make sure that it doesn't delete the data inadvertently. Does that answer your question? So would you start file 2 right now and show that there is a link to file 2? So no, stat file 2 doesn't know anything. So file 2 is actually, file 2 doesn't know anything. Whereas if you do, even though like file 2 duplicate doesn't, file 2 duplicate is just, it just says the symbolic link because it's a special kind of file. And here the inode number is different compared to file 2, but the data of file 2 duplicate is actually the name of the file 2. For instance, we can actually, we cannot actually open file 2 duplicate, because if you try to open file 2 duplicate, it'll just open file 2 because it's a symlink. Made hard link, that would show up the stat, right? Links would say, but if you made a hard link, that would show up under stat, right? Links would say 2. Yes, perfect. I like it. Let's do that. So let's create. Okay. Let's see. I'm now creating a hard link. Stat. Yeah. Jacob, does that answer your question? So the links to is the reference count. You're right. Perfect. So that's the hard link and soft link. Do you have any questions? So another interesting thing is what happens when you delete files, especially when you delete symbolic links. Okay. So here, let's say, what happens if I delete file 2, because file 2 duplicate is pointing to file 2.txt. Let's say if I delete file 2, okay. What happens if I delete file 2? when I do this, there is a broken link here. So operating system is trying to access file 2. It knows that file 2 doesn't exist. So basically it's a broken symbolic link. Okay? And so if you try to open file 2, duplicate, it doesn't work because it tries to open file 2, it doesn't exist. Let's say now I just create file 2 here. Okay, now if I try to do ls minus l, it says, oh, the link is present. Although I just recreated a new file, the file that I created, the file to which I created the symbolic link is different from the current file. Symbolic links just work fine because they reference by file name, not by the inode number. Okay. So, and you will get the same data if you do exactly, you see the same data. So another important use of symlinks is libraries. So you can see that there are different versions of libraries that you install, right? For instance, you have libc, libc 4.3, libc 4.8, different versions, they keep on coming, okay? And the versions have different file names. So how can operating system have a single file, but you don't need to change your applications, right? Most the applications that you build, it doesn't matter which version you install, somehow operating system uses the latest version. Okay, so the way it works is operating system creates symbolic links from the base file to the appropriate version. Okay, so for instance, like all the libraries will be stored here. If you see, for instance, let's look. Okay, you see, you see. So what operating system does is it actually creates, for instance, libgdi plus. It'll just, when you install it, it'll create a symbolic link. And when you keep on upgrading, it just changes the symbolic link to point to the latest version. Okay. So here you can see that the version of libnet pbm is actually 10. Okay. But operating system just maintains a symbolic link. That way, when you update to a latest version, it'll always just update the symbolic link. That way all the applications, they can just use this symlink file. You can always be safe that you're always using the latest version of the library without even changing any like dependencies, without even changing the dependencies in your programs. Okay. So let's see how we can create file systems. Okay. So example. Okay. So disk is just a storage unit, right? So let's mimic a disk. Let's create an empty file of, let's say, some 10 MB or something, and let's see how we can create file system assuming that that big file is the disk. Okay. So let's create a big file. So you can, dd is data dump, like, so you can actually, let me create an empty file which is filled with zeros. OF equal to IF is input file and OF is output file. So let's say file system. Say I create this thing. Block size is 512. Blocks equal to, let's say, 4096. Okay. Let's see what. And dd bs. Okay, count. I think it's the count. So here, dd is a command that helps us create big files easily. So here what I'm saying is read from dev0 and write to uh, file. There is a typo here. Write to file system.file and block with block size of 512 and write basically 4096 blocks where each block is of size 512. When you do this, cool, perfect. It created a file. Let's see. Perfect. It created, what's the size of the file? Okay, it's created a file of 2 MB. Okay. So let's assume this as our disk. Okay. So you can use, there are many makefs commands, like depending on the file system you want to create, like there is like ext3, makefs, fat, all these different commands that you can use to create different file systems. Okay, let's create a file system like ext3. So file system, like the difference between different file systems is the way that they store inodes and the way they modify the disk, so on and so forth. Okay. So let's create an ext3 file system on this file, assuming that file system.file is a disk. But to avoid confusion, let's rename that file system.file as a disk.file. Okay. Now let's create file system. Make ext3 on disk file. Okay. Perfect. So it created perfect. It created the file system on the disk, which is the disk.file. Perfect. It created inodes, it created superblock, everything. So if you look at how the disk file looks like, this is an hex editor. You can see there are various things that it wrote. Like the first is a superblock, and the rest all are like inode numbers, and the rest all are zero because everything is uninitialized. So these are all like bits. These are all ones. They indicate whether that inode is free or not. If one means the inode is free, zero means the inode is occupied. So everything is FFF here. So basically these are the bits that indicate whether the inode is free or not. So all inodes are free. That's why all these, you can see all FFF here, which is all ones. Yeah, so this is how a raw disk looks like. Okay. And now once you have a disk, you need to mount it because now in order to access the files in the disk, you need to mount it. How can you mount it? So you use mount. Okay. I want to mount disk file. Where should I mount? So let me mount, let me create a new, let me create a directory here. There. Okay. Wow. Okay. Mount directory. So basically here I'm mounting my disk to mount directory. Okay. Okay. So on Ubuntu, you cannot mount if you are not root. So let me, perfect. I mounted mount directory. It's empty. Okay. So now you can see, if you see df minus h, you see we actually mounted this to mount directory. So loop is loop device. Basically, when you mount a file to a directory, you get you see that as a loop device. Okay. So df minus h shows that we actually did mount. Okay. So let's create a file here. Let's say echo dummy file .txt. Okay. Okay, it's access denied because I think we did not give permissions. Like, okay, let's look at the permissions of this directory. Sure, only because we just mounted as root. That's why I'm not root, so I cannot. So okay, let me give permissions. Okay. Now let's write some string that we can see 469. Okay. Say instead of dummy file, let's say Purdue file. Okay. Perfect. We created two files now, and so let's unmount the mount directory. So to unmount, you just say mount. Of course, I need to do sudo. Okay, good. So now I unmounted the thing. So now when I go into the directory is empty because the file system just got unmounted. Now let's look at disk file and see what changed in the disk file. You should at least see we should at least see ECE469, right? Because we just stored that data into Purdue file, and Purdue file somehow should be in this file system. So let's open the X editor. Okay, let's try to search. Okay, search as text. Wow, it says search value not found. Okay, maybe it compressed or something. Okay, I think it did do some stuff. Okay. There are some changes here. Okay, that's it. Let's try to remount the file system again to see if our files exist in this disk. Okay. And okay. Okay, let's okay, let's mount again. Perfect. We still have files. Our files are still there, but somehow when we do a hex editor, the string ECE469 is not present. That could be because ext3 uses some encoding. It may not store the actual data, but it could store some encoding of the data, or it could actually compress the data. We don't know. That depends on the file system. It could either store the raw data of each file, or it could compress it could compress the data into some different format. And when you actually mount it, then depending on the compression used, it could display the correct data. Okay. So yeah, so this is how at a very simple level how file systems work and how to create file system. For instance, if you have disk lsblk is a command that can give you disk. For instance, there are many file disks that are based on files. These are indicated by loops, but there is one disk which is actually the real disk. This is my disk. So this is the flash disk of ssd that I have. And there are two partitions. Again, uh, partition is just like logical parts of a disk that helps us to save uh, different files in different partitions, or different file systems in different partitions. So partitions is just like logical parts of a disk, and you can actually load different operating systems in different partitions. If you have used very old, not exactly very old, I don't know if you done dual booting of your laptops before. Like you could have both Linux and Windows on the same laptop. So the way you do it is you create different partitions on the same disk. And on one partition there is Windows, On the other partition, there is Ubuntu. Okay. So, and yeah, that's basically how it works. And when you, let's say, when you have to create a file system, the things that you need to remember is like the structures that you need to think are like the inode structure. And oh, wow, my screen is just stuck. Okay. Wow. Can you guys hear me? Okay. Like, okay. Perfect. There is something wrong with my monitor anyways. So when you have to create a file system, the things that you need to think about is how can I create like how can I format the disk so that all the data that is needed to access the files is stored, is present somehow. Okay. So here, usually the way most of the disk system, most of the file systems work is they have some magic at the beginning, which indicates the type of file system. This could be ext3 or FFA, like whatever. And then once you have the magic, that will tell you like the type of the file system. And then depending on the type of the file system, you usually create file system module in the operating system. And once you see the type of the file system, you invoke corresponding module, which actually reads through the rest of the super block, and it tries to understand, okay, which blocks are the inode blocks, which blocks are the data blocks, so on and so forth. One each inode block, you read the inode block will tell you all the files that corresponding to that particular inode, or if it is a directory, it will tell you the data block that corresponding to that directory. And if you read that particular data block, you will get the inodes or like the file names corresponding to that directory, so on and so forth. So everything is just an indirection. So starting from super block, you can actually analyze the entire disk by making the super block as a pointer to inode blocks, and inode blocks which are pointers to other data blocks. Okay, that way you can create file systems on like any raw disk that is provided to you. Okay. And okay, I see some questions like difference between ext and fat. It's just for instance, fat, I'm pretty sure like the size, the maximum size of file is like 4 GB or something. But ext, there is no limit, like you can create huge file sizes. That's one limitation. And ext3 is in general fast. It's very well supported in Linux. And fat is also supported, but ext3 is most commonly used on Linux based systems because like the format itself is very nice. It has some performance advantages, like you can easily create a file, and like reading is okay, but writing is hard. Yeah, there are some advantages and disadvantages between different file systems based on how they use their inode and how they structure their data. So it is because difference in trees, you mean the directory trees, or I mean the difference is the way the file system organizes uh, the inodes and data, right? Exactly, data structure for implementing. Yeah. And I mean, another interesting way to, for instance, like if you want to test a file system, like what is the best way? The best way, what's the best way? Try to create like as I just showed, try to create a file system using like mk like mkfs commands, and then try to flip certain bits in that file that you just created, which is actually a disk, and now try to load that by using mount. If mount fails, or like if the operating system crashes, then most probably you found a bug in the file system implementation. because as you can imagine, there are a lot of these interconnected data structures inside the disk. So if the file system is not exactly verifying certain data, if it is blindly trusting some data in the disk, then it could actually go past the disk, or it could like it could basically do like you can do buffer overflows by modifying certain values in the files in the disk. So race conditions can be used to change privilege of file system nodes. Yes, I mean there are like the classic race condition is time of check to time of use. I remember having a question, like I added that question in the midterm, where yeah, file system operations themselves are not like file system operations are atomic. However, consecutive file system operations are not atomic. So especially in the presence of symlinks, so you don't know whether you are accessing the file that you are supposed to, because an attacker can change, like can keep the file name, but can change the symlink, can change the file, like can make the file as a symlink. That way your program might think that it is accessing certain file, but although because of symlinks you are actually accessing something else. So you need to be really careful if you are writing, like if you have written some like security sensitive programs, for instance turn in, or like these kind of programs which actually read files from the file systems, like you need to make sure that you're not reading some symlink and accessing some file that you are not supposed to access. So okay, any other questions? Okay, so if not, that's it. Okay, sorry it got delayed. I'm sorry for the slowness of my computer. Yeah, that's it. Thank you.